So imagine that you have a three-dimensional coordinate system like so. And there is a curve in this space. So this is a curve C, and at one point you have a particle, and the particle is moving on this curve, and you pick up a point right here. We call it point P. Actually, let's pick it up right here, point P right here, and this will be point Q, the second point. And the vector, the position vector that is corresponding to the point P is R of t, and the position vector corresponding to the point Q, and there is a time difference. Okay, this is P of t, so this is a point at time t, and this is Q at the time t plus h. So this vector, the second vector, or the position vector, will be R of t plus h. Now, if we are looking at the average velocity between the 2 points, in other words, the average velocity over a period of time that measured as h, where the particle moved from P to Q, then the vector that represents the difference is this vector right there. Okay, and this vector we're gonna use that. So this will be the vector delta r. Okay, which is r of t plus h minus r of r minus r of t. So we'll write here delta r will be r of t plus h minus r of t. I'm sorry? Well, right now we have 3 and that's it. I promise no more errors on this one. Now we're going to define let v sub 1, and this is a vector, equals the average velocity or average rate of change of r on a time interval h. Remember, in this time interval, the particle is moving from P to Q. Okay. So, what will be that particular the average velocity? What will be the expression? Let me split, move to the next page, and show you what I mean by that. Well, h is in units of time, right? And so we're going to say that the vector v, the average velocity, would be simply the difference quotient, the same way when we did it with real valued functions. So it will be r of t plus h minus r of t, which is the numerator is delta r, and the time interval is h, right? So you have this expression delta r over h, and the instantaneous velocity will be the velocity vector. So let v of t, this is v1, I just gave it v1 to make it distinct from other vectors. That's all. It can be v0 or anything like that. Let v sub t be the instantaneous rate of change of r, or the velocity vector. So the point I'm making is all the theory that you learn in Calculus 1, okay, this will be given by the limit. So because we are talking about instantaneous rate of change, we're going to say that v of t will be the limit as t approaches 0, as h approaches 0, where the time interval approaches 0, of r of t plus h minus r of t, or at the time t, divided by h. And this, by definition, is r prime of t. So here is the evidence why the instantaneous velocity is the derivative of the vector r. Okay, as the derivative of vector r represent instantaneous change between r in r over infinitely small amount of time h. So this is the limit definition of the velocity. Again, by default, if we don't say average velocity, we mean instantaneous. And of course, Roberto mentioned that the speed is the magnitude of the velocity. So we're going to say that speed equal the magnitude of v of t, like so. What about the acceleration? Well, acceleration is the rate of change, the instantaneous rate of change of the velocity. So it will be the derivative of the velocity. And remember, this is a vector, and it's a vector is a vector it's a vector function in time, and we can write it as the second derivative of the position vector r. I want to give you an example that does it in reverse. Roberto took a velocity, a position vector, and differentiated it to give us the velocity and the speed. You didn't give us the acceleration, Roberto, did you? All right. What I want to do, I want to go and do the reverse part. I want to find the position given the acceleration. Okay, so in this example, we'll work it in reverse. Okay, the acceleration of a moving particle is given by the following function. So this is a vector function, and it's 4ti plus 60j plus k. And what we know, the initial velocity and acceleration, initial velocity and position. So the velocity at the time of 0 is simply I minus j plus k, and the position at the time 0 is 4ti, no, is simply I. That's it. Just I. Find the velocity and position. Find the particle's velocity and position. In other words, we'll have to integrate. So this exercise is really a calculus 1 exercise, except we do it with a vector value. All right. So since we have the acceleration, we're going to say that the velocity will be the integral of the acceleration vector. So we integrate term by term, and we have 2t squared in the I direction plus let me look at the data, 40i, 60j, and k. Okay, at least that's what I have. Or you think it should be different value?
No, I'm thinking of like normal searches.
Yeah, I don't have the this particular example here. So let's continue with this one. So we have 4t squared I, and then we have 3t squared j plus tk plus some vector c. Okay? So how are we going to find the vector c? Well, we'll see what happens when t equals 0. So v at 0, if you put everything, you replace everything with 0, all those the ijk term disappear, and what you have is that vector c, and you know from the data that it's I minus j plus k. Okay, so put this together, and you have v of t will be, in the I direction, we have 2t squared plus 1. In the j direction, we'll have 3t squared minus 1. And in the k direction, we'll have t plus 1. And that's how you eliminate the constant vector c. Now, to find the position, we integrate one more time, and we have this will be 2/3 t cubed plus t in the I direction, t cubed minus t in the j direction, and t squared over 2 minus plus t in the k direction, plus and let's call this C1, and now we have C2. Okay. Again, we check what happened at the initial position. Well, R sub 0, everything else will go to 0. Yes, because we have only term containing t. So 0i, 0j, 0k, and what we have is this constant vector C2, and it's equal to I. Okay, so finish this up. R of t equals, in the, we have only the I component to add, so it will be 2/3 t cubed plus t plus 1 I, and then the rest will remain the same, t cubed minus t in the j direction, and t squared over 2 plus t in the k direction. And this is the result. So we have the position, and also we found the velocity. As I said, this is a straightforward, there is no new technique here. I just want to emphasize that even if you have indefinite integral, if you have the initial position or any other position, it's convenient to work with initial value. What happened when t equals 0? Because a lot of time stuff disappears. But if we had the position at the, or the velocity and acceleration at the velocity and position at t equals 4, we still could have found the value of the constant C1 and C2 and replace those. All right, folks, thank you so much. We meet again on Friday here.